Hello and happy Monday. So to start off with today, we're going to look at the schedule that's posted in Google Classroom and go through each day and the assignments. So today you're watching this video on the period of a spring math system and taking notes. When you're done with the video, you will fill out the Google form. Those Google forms count as homework grades. Okay, and on a test or quiz, you should have the work and the questions written down in your notes so that you have something to utilize. Okay, sorry, for your tests. For tests, you're going to need to have these written down in your notes, have the work written down so that you can utilize them on your actual test. The Google form is due by tonight at 5 p.m. Okay, tomorrow in class, we will take a look at a spring math system. You'll watch a video explaining how to do the lab digitally and how to record the data. You will then complete that lab. The suggestion is that you coordinate with your group and do a Google Hangout during your class period on Tuesday when you are completing the lab. This lab should take no more than an hour. Okay, if you work consistently, but it is technically due on Wednesday night by 5 p.m. So assign Tuesday morning, due Wednesday night by 5 p.m. You'll find it in Google Classroom under Spring Math Lab. Okay, so those daily Google Forms and the submission of your labs count as the daily attendance. On Wednesday, your attendance grade will come from, or your attendance mark will come from attending the Google Hangout during your class period. So we will do this every Wednesday. On Wednesday, we will play Kahoot during your class period. So you must, during class on Wednesday, attend the Google Hangout. The invitation will be sent to your school email. On Thursday, we're going to have our frequency, pendulum, and period quiz. So we're going to talk about finding general frequency and general period. Okay, which would be that first Google form from introduction to vibrations, and then the period and frequency of the pendulum. Okay, so that quiz will take place during your class period. You must join the Google Meet. You can use your note card and your calculator, just like every other quiz. You'll join the Google Meet, then you'll open up the Google form in Classroom and you'll take the quiz. This must occur during your class period. It is due at the end of your class period. Okay, if you have any questions, feel free to add it to the Google form for today. But on Wednesday and Thursday during your class period, you will be Google Meeting with me. On Friday, your assignment is to watch a video on the frequency of a spring math system and take notes. Fill out that daily Google form, which is due by 5 p.m. on Friday. Okay, so do now for today. Today we're going to be talking about a new type of simple harmonic motion and a system in which follows simple harmonic motion. But before we get started on that, you're going to try this do now as a nice warm up for today. So a pendulum is vibrating with a frequency of 2 Hertz and has a length of 1.5 meters. What is the acceleration of gravity on the planet that this pendulum is vibrating? Okay, so you have the frequency of the pendulum and the length. You need to find the acceleration due to gravity. So you're going to pause the video and calculate the response for the do now. So pause the video. Okay, so you're going to enter the response to this do now, meaning the answer to this do now. You're going to enter that into the Google form at the end of today. So make sure you start this in your notes. The first question on the Google form is asking you for the answer to this do now. Okay, so we know that pendulums follow simple harmonic motion. How do we know that they follow simple harmonic motion? Well, we know that simple harmonic motion is repeated oscillations or vibrations. Okay, what is an oscillation or vibration? If you take a look at your notes from the Introduction to Vibrations video, you will have written down that a vibration, also known as an oscillation, is the back and forth movement about an equilibrium position. Okay, so if it moves, oscillates between two positions, a positive and negative position about an equilibrium point, it's oscillating. If it does this repeatedly, it's moving with simple harmonic motion. We know that objects move with simple harmonic motion due to a restoring force. Okay, we discovered a little bit about that restoring force with the ruler, okay, as we moved through that lecture. So let's take a look at this system. Okay, and let's see if it follows simple harmonic motion. So we're taking a look at a mass spring system. So you have a mass attached to a spring. That mass is pulled either to the right or down by an amplitude or displacement of 2.5 centimeters. So it's pulled down 2.5 centimeters and then released. Once the mass is released, it's going to move up and down. We take a look at our vertical spring mass system on the right. It's moving up and down about a position in which it both begins its motion and ends its motion. If we take a look at the spring mass system on the left, the horizontal spring mass system, when the mass is pulled to the right and released, it's going to move back and forth about some equilibrium position. So when a mass is attached to a spring, stretched to an amplitude, and released, it moves back and forth or up and down about an equilibrium position. Is this simple harmonic motion? Yes. Okay, so quite literally, that is the definition of what a vibration or an oscillation is. The mass repeats its motion, its vibration, its oscillation. Okay, so the mass repeatedly oscillates. If we're talking about the spring mass system on the right, it's moving up and down about an equilibrium position. We're talking about the horizontal spring mass system on the left, it moves back and forth about an equilibrium position. Okay, in both cases, that is the definition of what an oscillation is. So a spring mass system will follow simple harmonic motion. How can we measure simple harmonic motion? So how can we measure the motion of this spring mass system? The same way in which we would measure the motion of any object in simple harmonic motion. We can determine its frequency and its period. So let's do that first experimentally. So if we were to attach a spring to one of the supports in the back of the room at a lab table. From that spring, we then attach a mass. We stretch the mass by 2.5 centimeters, and then we release it. So as you can see on the right-hand side, it's going to oscillate, move up and down about an equilibrium position. If we time how long it takes from the moment we release it to return back to that release point, which would be one vibration, the timer designates that it would take 0.77 seconds for one complete oscillation. Okay, so we know that our period is 0.77 seconds. Okay, to find the frequency, we know that frequency is the inverse of the period. So if we take 1 and we divide it by 0.77 seconds, we get 1.2987, which we can round to 1.3. Our units are cycles per second, or vibrations per second, which is the definition of hertz. So the frequency is 1.3 hertz, which means that it makes 1.3 cycles per second. The period is 0.77 seconds. So it takes 0.77 seconds to create or complete one vibration. Okay, so we can measure the period and frequency of the spring mass system because it is vibrating. It follows simple harmonic motion. What variables do you think the period and frequency of a spring mass system would rely on? So in a pendulum, we know that the period of a pendulum relies on what? If you take a look at that equation, right, for the period of a pendulum, it's 2 pi times the square root of L over G. So a pendulum relies on the length of the pendulum string and the acceleration due to gravity. The mass attached to the pendulum does not affect its motion at all. In a spring mass system, the variables that impact period and frequency are different than for a pendulum due to the diversity of the system. So things that are going to affect the period of the spring mass system is not the length of the spring, because that varies with every second. Instead, it varies on or relies on the stiffness of the spring. Okay, so one factor that will impact the measured period or frequency of a spring mass system is how stiff the spring is, the stiffness of the spring. We call the stiffness of the spring the spring constant. So in other words, it's a constant value that is a measurement of how stiff a spring is. That constant will describe how much force is required per 1 meter of stretch. So how much force must be applied to stretch the spring by 1 meter. That is the spring constant. So if it's the amount of force per meter of force per meter of stretch, what do you think the units are for spring constant? So force we know is measured in newtons. Stretch or displacement is measured in meters. So the units for spring constant are newtons per meter. It describes how difficult it is to stretch a spring, how much force per meter of stretch is required to stretch or displace a spring. And that will affect how quickly a spring mass system oscillates. The other factor that will impact frequency and period of a spring mass system is the actual mass attached to the spring. So unlike a pendulum, which vibrates back and forth, a spring mass system vibrates up and down. The amount of stretch is reliant on the mass that is attached to the spring. So it will affect how quickly a system will vibrate. So the mass attached to the spring is another factor which will implement or impact the period of frequency. And mass is measured in kilograms. Okay, so our equation for spring mass system in which oscillates back and forth about some positive and negative amplitude. In our example, it was 2.5 centimeters. So our spring mass system oscillates back and forth about an equilibrium position measured as 0, according to this equation. So the period of a spring mass system, capital T sub S, is equal to 2 pi times the square root of m over k, where T is the period measured in seconds, m is the mass measured in kilograms, and k is the spring constant measured in newtons per meter, which is equivalent, newtons per meter is equivalent to kilograms per second squared. In our next example, we'll prove that using dimensional analysis. Okay, but a newton per meter is equivalent to a kilogram per second squared. We label spring constant as newton per meter because of its definition. It's defined as the amount of force required to stretch a spring by 1 meter. Okay, so we label it based on its definition, but dimensionally, a newton per meter is equivalent to a kilogram per second squared, which we'll prove in our next example. Okay, so let's take a look at how we would apply this equation. So let's say that we're given a situation, right, where we can't just displace the pendulum or spring mass system, okay, and find the period or frequency. Okay, we'd have to use this equation. So if we can't physically test it out in lab in real time, we would need to use this equation. Or if we're given period and we need to determine the mass or the stiffness of the spring, we can use this equation. Okay, so if we can't physically determine T in an experimental situation, or we need to find mass or spring constant, we would need to use this equation. So let's take a look at an example. So this is our third example for simple harmonic motion. Example 3, mass and spring system. So you have a 10-gram mass attached to a spring. It is displaced by 0.2 meters and released. Okay, so this is technically the amplitude. 0.2 is technically the amplitude. As we know from lab and our previous 2 homeworks and our previous 2 lectures, amplitude does not affect the period or the frequency. The reason why they tell you the amplitude is to signify that the system is vibrating. If you displace a system from an amplitude, it's vibrating. If you do not displace the system, it's going to remain at rest. So although the amplitude does not affect the period or the frequency, sometimes they include amplitude in there to give you an idea that it is vibrating or oscillating. Okay, but you technically don't need that information. A student finds that it takes 3.2 seconds for 5 oscillations. Okay, so a student times it out. They count 5 oscillations. The time that they record is 3.2 seconds. What is the spring constant? Okay, so given the mass of the system, which is 0.01 kilograms, the amplitude, 0.2, the time for 5 oscillations, which is 3.2 seconds, they're asking us to find the spring constant, K, equals question mark, which is the stiffness of the spring measured in newtons per meter. In order to find K, we need to first find the period. We know that the period is the time it takes for 1 oscillation or vibration. We're given the time for 5 oscillations. So our first step after we change our units from grams to kilograms, right? Mass must be measured in kilograms always. We have to find the period. So step 1, period equals time per oscillation. We take 3.2 seconds. We divide by 5 oscillations. You get 0.64 seconds, which is the period of the spring mass system. Okay, and the time it takes for the spring mass system to make one complete vibration. Now that we have period, mass, we can find the spring constant using the equation for period of a spring mass system. So you know that the period of a spring mass system, capital T sub S, S stands for spring, is equal to 2 pi times the square root of mass divided by spring constant, K. So we need to plug in what we know. We're going to take 0.64 seconds, set that equal to 2 pi times the square root of 0.01 kilograms divided by K. In order to get K by itself, we must get it out from underneath the radical. To get rid of the radical, we must square both sides of the equation. We square each term on both sides of the equation. So we're going to square 0.64 seconds and the entire quantity 2 pi times the square root of 0.01 kilograms over K. When we square 0.64, we get 0.4096 seconds squared is equal to 4 pi squared times 0.01 kilograms divided by K. Again, the biggest mistake the students make in this unit is the algebra. So I suggest that you follow this procedure for solving. If you use this procedure for solving, you will get the correct answer every time. To get K out of the denominator, we need to multiply both sides of the equation by K. It will simplify to 0.4096 seconds squared times K equals 4 pi squared times 0.01 kilograms. To get K by itself, we divide both sides by that period squared. In your calculator, to find K, you must type, if you look at the bottom left-hand side of the screen, parenthesis 2 times pi squared times 0.01 close parenthesis divided by 0.4096. You must put the entire numerator in parentheses and include a multiplication symbol between 4 and pi. If you do not, you will get the wrong answer. You must type it in this way into your calculator because your calculator does not know order of operations. So you must tell it what to do first. So you're telling your calculator to multiply the numerator first, take the product and divide by 0.4096. So please type it in your calculator as shown below. You should get 0.96. Our units, if you see, are kilograms per second squared. So here's the point where we prove that kilogram per second squared is equal to a Newton per meter. Okay, so a kilogram meter per second squared is equal to Newton per meter. So if you start out with Newton per meters, a Newton, if you think about F equals ma, a Newton is a kilogram times meter over second squared. Right, mass times acceleration, kilogram times meters over second squared. We're dividing that by meters. So you have kilogram meters per second squared divided by meters. The meters will cancel out, and we'll have kilograms per second squared. So dimensionally, a Newton per meter is equivalent to a kilogram per second squared. But we label K with Newtons per meter due to its definition. Right, the definition of K, the spring constant, is the stiffness of the spring. It describes how much force per 1 meter stretch is required. So K we found is 0.96 newtons per meter. So that means that it requires 0.96 newtons to stretch that spring by 1 meter. Okay, we determined that using the period of the spring mass system equation. Okay, so before you guys get to the Google form, in which you're going to try one more of these, let's talk about the quiz on Thursday. So on Thursday, you're going to have a quiz. It's going to be about 10 questions via Google form. The quiz is on finding frequency and period. Okay, so introduction to vibrations. So given the period, find the frequency. Given the frequency, find the period. Okay, given number of oscillations, find the period, find the frequency. The other section of the quiz will contain questions about pendulums. Okay, so finding the period or the frequency of a pendulum, answering conceptual questions as to whether the period or frequency would increase or decrease when certain variables increase or decrease. So it's going to be about 10 questions via Google form. You must join the Google Meet and take the quiz during your class period. Resources to study. You're going to want to take a look at the Google Forms from Monday, Thursday, and Friday of last week. Okay, you have the results sent to your email, your school email. You also want to take a look at the Kahoot that's posted in Google Classroom that we played last Wednesday. So the Kahoot and those Google Form questions, if you can do those and you have no issues, you should be fine. If not, attend after school help, okay, to get that sorted out before the quiz on Thursday. All right, guys, have a nice day. I will talk to you tomorrow.